Hi guys. Today we will be studying about minimum spanning trees, its applications, and two greedy approaches, namely Kruskal and Prim's algorithms to find such trees in a given graph. For more details, I highly encourage you all to read chapter 23 of your main textbook. In our previous lecture, we covered some fundamental topics on graph theory. We learned the handshaking principle, followed by efficient representations of graphs. We saw that for sparse graphs, using adjacency lists is more appreciated, whereas adjacency matrices serve efficient when the graphs are dense. Then we saw two graph search algorithms. The first was BFS, or breadth first search. This algorithm basically searched all equidistant neighbors of a vertex first before visiting the neighbors of these neighbors. The DFS, on the other hand, does a depth first search from a given vertex and then visits the first order neighbors of that vertex. DFS was applied to topologically sort the vertices in a directed acyclic graph based on the finishing time of traversal. Also, we saw how DFS was used to find the strongly connected components in Kosaraju's algorithm. The topic for today deals with weighted undirected graphs that are connected. By weighted, I mean that the edges or links between any two vertices in the graph carry some value. This can be interpreted as the cost of creating such an edge. For instance, in circuit design, the wiring cost between pins can be considered as the amount of wire needed, or in communication systems, it can be the bandwidth of a link. In roadway maps, it can be the length of the road connecting two cities. To state our problem formally, let us denote a connected undirected graph by GVE, where each edge UV in the set E has a weight which is given by WUV. Our goal is to find an acyclic subset of edges denoted by T that connects all the vertices in the graph G and yields the minimum total weight. In other words, the sum of the weights of the minimum number of edges needed to connect all the vertices in the graph G should be minimum among all possible ways. Putting it mathematically, this is what the expression would look like. Carefully studying the problem statement tells us that this subset T should therefore form a tree that spans over the graph G. Therefore, such a tree is called a minimum spanning tree. A graph may have more than one minimum spanning tree. What we want to do in this lecture is to find such trees. Over here, we see an example of a minimum spanning tree, or MST for short. As shown in this figure, the edges carry some weights, and the shaded edges form an MST for this graph. Adding up the weights on the shaded edges gives us a total weight of 37. Now, is this MST unique? What happens if I remove the shaded edge BC and replace it with the edge AH instead? We see that it gives us another MST with minimum weight of 37. So this graph has more than one MST. Today we will cover two greedy algorithms to compute MST. We assume that the graphs under study are connected, undirected, and have weighted edges. Both algorithms that we will be covering shortly follow the following general strategy to gradually build an MST. The approach basically manages a set A of edges that satisfies the following loop invariant at all times. At the beginning of each iteration of the while loop shown over here, the edges in subset A form some MST. Using this strategy, what we do is we find and add an edge, say UV, in each iteration to the subset A such that A union UV would result in part of an MST in the graph. Such an edge is called a safe edge as it maintains the loop invariant at all times and becomes part of the final MST that we are looking for. The challenge over here, however, is finding such safe edges. Before we start with the algorithms, we need to get a few definitions out of the way. We begin with defining a cut of a graph. A cut essentially is a partition of the vertex set V. That means a cut divides the set V into two disjoint sets, S and V minus S. Next, we say that an edge UV crosses the cut SV minus S if and only if one of its endpoints is in S and the other endpoint is in V minus S. Furthermore, a cut is said to respect a set A if none of the edges in set A crosses the cut. And finally, a light edge is an edge crossing a cut such that it has the minimum weight among all other edges that cross the same cut. There are two ways that you can view a cut in a graph. Let's look at figure A. Over here we see a nonlinear line, this line, which actually divides this graph into two subsets. One subset containing the black vertices and the other subset containing the white vertices. Therefore, we can consider the black nodes as set S and the white nodes as set V minus S. Therefore, this nonlinear line is a cut of this graph. Every edge that connects a black node to a white node actually crosses this cut. So edges AH, BH, BC, DC, DF, and EF are crossing the cut. Among these edges that are crossing the cut, we'll find the edge which has the minimum weight. So looking through all these edges, we see that DC has a minimum weight of 7 among all of them, and therefore it is called a light edge. Now, if you want to find a linear cut, all you have to do is put the black nodes on one side and the white nodes on the other side and draw a straight line. This again gives us a different view of the cut as shown in figure B. As mentioned earlier, once we are able to identify the safe edges, the rest is straightforward. The two algorithms that we will look at today adapt the following rule to efficiently find such safe edges. The rule is postulated as the theorem given here. It states that for a graph G with set A and some cut SVS that respects A, if edge UV is a lightweight crossing the cut, then this edge is safe for set A. The proof is very simple. First, let us assume that there is an MST denoted by T that includes all the edges in set A and does not include the light edge UV. If T includes the edge UV, then there would be nothing to prove. Now, let's build another MST called T prime that includes all the edges in A as well as the light edge UV. As we see in this figure over here, the nodes U and V are on opposite sides of the cut. That is, node U is in set S and V is in set V minus S. And that's why they have different colors. So, if T is an MST and does not contain the edge UV, it implies that there should be some other edge along the path P that connects U and V, shown here, that crosses the cut. Otherwise, it would not form an MST. Let this edge be called XY. This edge XY is not in set A though, because we said that the cut respects A. So, if we remove edge XY, it would break T into two parts that are not connected. If we add edge UV to connect the two parts, it would form a new spanning tree denoted by T prime as shown here. What remains now is to show that this T prime is in fact an MST. We know that edge UV is a light edge crossing the cut, and edge XY is another edge that also crosses this cut. Therefore, since UV is the light edge, the weight of UV would be lesser or equal to the weight of XY. When put in the weight equation seen earlier, we would get this. Therefore, the total weight of the spanning tree T prime would be equal to the total weight of the spanning tree T minus the weight of XY and adding the weight of edge UV. So this would be less than equal to the weight of the spanning tree T. But we assumed in the very beginning that T is an MST and there cannot be a spanning tree with total weight lesser than T. Therefore, the weight of the spanning tree T should be equal to the weight of the spanning tree T prime, which implies that T prime is an MST as well. Finally, we need to show that the edge UV is actually a safe edge for set A. By now, we know that set A is a subset of the spanning tree T prime. And since edge XY is not an A, the union of A and the edge UV would also be a subset of T prime. But we just saw that T prime is an MST, which concludes that the edge UV is safe for A. Now it's time to look at how the two greedy approaches that are built on the generic MST strategy find an MST in a given graph. Let's start with Kruskal's algorithm. The intuition behind this approach is that initially the set A is considered to be a forest where each vertex is a tree. Then the algorithm gradually constructs the spanning tree by finding a safe edge connecting two trees in the forest that has the least weight. Looking at this pseudocode over here, we see that we create trees rooted at each vertex in line 2 after initializing set A to be an empty set. On line 4, we sort all the edges in the graph in the ascending order of their respective weights. Then, in the for loop on line 5, we select each node UV in the sorted order and check if vertices U and V are connected or not. If U and V are not connected, we then add the edge UV to the set A and connect the vertices U and V using union function on line 8. Once we create a tree containing all the vertices, we return the set A, which ultimately contains the edges that form an MST. Using this graph as an example, let us explain how the Kruskal algorithm works in simple words. The first thing you need to do is to search for the edge with the least weight. If there are multiple edges having the same weight, then select any one randomly. In the beginning, none of the edges are shaded, meaning that each vertex is the root of its own tree. If the light edge that you select connects two distinct trees, then shade that edge and put it in set A. So in figure A, we see that the node H and node G are connected by the light edge of weight 1. So we shade this and we add the edge to the set A. Then we search for the next edge which has the least weight. That would be edge connecting C and I. Since these two trees are not connected, so we select this edge and highlight it. Then we look for the next edge, which would be edge GF. We could have chosen GF before CI, but since both of them have the same edge, we can choose any one randomly. And we keep doing this until we reach this graph shown in N. Over here, we see that we finally get a minimum spanning tree where the edges that are shaded are shown in this figure. The next algorithm is the Prim's algorithm. Note that in Kruskal's algorithm, the light edge added in each step does not necessarily result in a connected tree at the end of the step, but instead may result in a forest of trees which eventually would be merged into a single tree that represents the final MST. In Prim's algorithm, however, the edges added to set A in each step results in a single tree that grows gradually. The algorithm works as shown here, where the graph G and some arbitrary vertex R is given as input. The vertex R will be the root of the MST that eventually emerges. During the execution of the algorithm, all vertices that are not in the tree reside in a min priority queue denoted by Q based on a key attribute. For each vertex V, the attribute v.key is the minimum weight of any edge connecting V to a vertex in the tree. So by convention, v.key would be equal to infinity if there is no such edge. The attribute v.pi, on the other hand, indicates the parent of V in the tree. Now let's see how Prim's algorithm works using an example. Suppose we are given the graph in figure A and the vertex A as the root to begin from. So there is a cut that separates vertex A from the other white vertices in the graph. This is that cut. Next, we find the light edge crossing this cut. There are two edges here, AB and AH. Between these two, AB has a lower weight of 4. So we select this and add it to set A. Now the vertex B is made black, thus placing it with vertex A in one set and the other white vertices in another disjoint set. The new cut separating these two sets can be drawn like this. Now we have three edges that cross this cut, AH, BH, and BC. Among these three, AH and BC have the same weight of 8, so we can choose any one randomly. In this example, we choose BC. So we highlight BC and we make the vertex C dark. Now we have a new cut, which would be this. And we find the light weight crossing this cut and keep adding it to this graph. So as we continue, we finally reach figure I, where we see that we find a minimum spanning tree that connects all the vertices in the graph such that the weight of these edges is the minimum. The running times of both the algorithms is the same and it's found to be of the order E log V.